Hello students, welcome back. In the previous videos, we had some review on Module 7 materials, and then we defined kernel and images. And kernel is element of vector space V, so that f of that vector is a zero vector. This is causing confusion, so let's remove that. And clearly you can see that this is a subset of V because arbitrary element of kernel is of this form, V in vector space capital V, and then the condition is f of V is equal to 0. Now how about the image? Image is set of image vectors. These are original vectors, and then it is sent to image vectors, f of V. It's set of f of V's basically, and f of V belongs to the target. So image is a subset of W. You can clearly see that. By the way, in calculus or below, we used to call the image the range of f, but we don't use the term range anymore in this course. Let us call them image. And then also f of V. In calculus, we used to call those kind of things function values. Same way in college algebra courses or pre-calculus or things like those. That was because all the functions we have been dealing with in calculus level was real functions. So the target was a set of real numbers, so it's a value. But then again, in this case, target is not a real function, real number system. Excuse me, the target is a vector space. So value, the term value is not very good, even though I can still use it. The term I prefer to use is image. So this is image set or image space, and this is image vector because it belongs to a vector space. It's a vector and it's f of something, so it's an image. So image vector. So image of f is basically the set of image vectors. And we proved that kernel is a subspace. We did this. And then we have yet to prove that image is a subspace. So this is image set at this moment. And soon we are going to call it image space because we are going to prove this is a subspace shortly. Okay, how do we prove? We have to prove these three. So if I have, not V, W1 and W2 belong to image, then so closed under addition, that's something we have to prove. And then closed under scalar multiplication, and C times W, scalar multiplication, belongs to the image set. And finally, zero vector. It's a zero vector in vector space W because image is a subset of W, but then again, it's a bit confusing. So let's just write like this. So these three are something we have to prove. Okay, which is easiest? The easiest, of course, is the third one, zero vector. So let's begin with that. So does the zero vector belong to the image? What do you mean by image? It's a space of function values or image vectors. So f of zero vector is, as a matter of fact, f of zero vector. To be a little more precise, this belongs to vector space W, and this belongs to vector space V. Therefore, zero vector belongs to the image. And okay, let's bring back this W here. And if you don't like these subscripts here, W and V, just remove them all and just use capital O. That'll be fine. Now, how about these two? Let's prove these, but before that, let's make some observation. You see, image of F is subset of W, so arbitrary element of image is of course W's, but as a matter of fact, if you go back to the definition of this image, the arbitrary element of image actually looks like this, F of V's. It comes from a certain original from V. So instead of just W and W2, as a matter of fact, we can start with V1 and V2. So W1 is F of V1, and W2 is F of V2. And then we have to prove that W plus W1, W1 plus W2, excuse me, is in the image set. That is, can that be written as F of something here? Well, let's figure it out. And then, using the properties of linear map, you can rewrite like this, right? So, is this sum a form of F of some vector? Yes, indeed, we got it. Therefore, W1 plus W2 sum belong to the image set. So closed under addition, we are done. Can you do something similar for the second claim here? Closed under scalar multiplication. What do you mean by W is equal to image of F? Arbitrary element of image looks like this, F of something. So W is F of something. Therefore, C times W is equal to C times F of something, isn't it? And can you use a property of linear map and write like this? Can you do this? Sure you can. And then, did we express this successfully in this form, F of certain vector? Yes, indeed, F of certain vector. Therefore, the C times W, the scalar multiplication, belong to the image. So closed under scalar multiplication as well. And there goes the proof. We have to prove these three. Closed under addition, and then we have it. Closed under scalar multiplication, we have it. And zero vector, which is not really necessary, but here we go anyway. By the way, how did you do it in my notebook here? Again, instead of using 1, 2, 3, I just used a single condition using linear combination. W1 is F of V1, W2 is F of V2, because that corresponds to the definition of the image, set of all the image vectors you see. And then apply the linear combination. AW1 plus BW2 you can rewrite it as f of the linear combination, and therefore the conclusion. The linear combination can be written as f of a certain vector. Yes, it is an image set. So we have two versions. One is using linear combination in a single step. The other is using three-step process. Which one I prefer? Actually prefer this longer version, this 1, 2, 3 version. Okay. Done with kernel and image. Do we have time for some examples? Okay, let's begin. Determine the kernel of a linear map from R3 to R2 associated with a matrix. And what's the matrix here? Okay, 3, -1, 3, 0, -1, 1. So what conclusion can I draw from here? L of L of E1 is 3, -1. L of E2 is 3, 0. And L of E3 is -1, 1. Do you see that? This is a matrix expression, and each column corresponds to the coordinate expressions of the image vectors of the basis. Okay, E1 is going to 3, -1. E2 is going to 3, 0. E3 is going to -1, 1. What else can we deduce from here? The linear map looks like, the linear map looks like this. L of V in general is equivalent to the matrix expression times the column vector. So let's see. No, let's write it like this. W equals L of V. That expression is equivalent to y equals to ax expression. Okay, so y is equal to ax expression. Let me use one more. And then x is arbitrary vector from R3. And then y is the image vector from R2. So y should be of this form. Something. And then about the x, well, okay, I'm gonna need another expression here. Give me a moment, please. So we need 3 rows. Okay, here we go. It's of this form. So y equals to ax. And then arbitrary vector, let's write it as x, y, z. And then this one, I'm kind of running out of characters. Okay, I'll just leave those as blank. For a short moment, I thought about introducing some Greek characters here, but that'll make this problem unnecessarily complicated. So that's what the matrix expression is all about. Now this problem is about kernel, isn't it? It's a kernel. So the L of V has to be equal to 0. Has to be 0 vector. So this has to be the 0 vector. In other words, this has to be the 0 vector. Make sense? So this one is the general case for the linear map. Yeah, any kind of linear map from finite dimensional to another finite dimensional has matrix expression, and matrix expression explicitly given, and those are related to the column, column, and column. Here in this problem, I gave you the matrix, but I could have equally as well given you these three so that you find out the matrix and then get this form. I could have done it like that if I wanted. In the end, I'm looking for kernel, so the y is equal to 0. So that's what you're looking for. That's the equation you're looking for. So okay, let's go ahead and do that. And then let's go ahead and do our computation. In the end, we have to have 2 by 1 matrix. So this row times column, so we get 3x plus 3y minus z. And then this row times the column, so negative x plus 0y plus z. That's it, isn't it? So what do you have? We have 3x plus 3y minus z is equal to 0, and negative x plus c is equal to 0. We have this system of linear equations. Looks like this can be solved rather easily. From the second equation, you can get z equals to x. And then plug that into the first equation. I'm going to get 3x plus 3y minus x is equal to 0. 2x plus 3y equal to 0. 3y is equal to negative 2x. I'm almost there. Y equals to negative 2/3. Okay, there you go. So we got what we wanted. What do you mean by the vector x, y, z belong to the kernel? That means x, y, z is equal to, x can be arbitrary, z is equal to x, and y is equal to negative 2/3 of x. Or I can take x out, and then this is gonna be 1 and negative 2/3, and then 1. I guess that completes the problem. All the vectors parallel to this direction, 1 comma negative 2/3 comma 1. If you're good at 3D geometry, then you will see this is a line. But we're not going to cover 3D geometry in this course, as a matter of fact. 3D lines and planes, we do those in Calculus 3 or multivariable calculus. So I'm not going to go any deeper, and then instead I'll just show you a picture. By the way, here's a solution. Looks a little bit shorter because I did my computation a little bit more effectively here. You see, the same conclusion I had before. And then I use a bit of a change of variable here. I remove the denominator. It's the same deal. And then here's a visualization. I hope you can see it's a line. We have this gray coordinate axis, x, y, z axis, and then a line. All the vectors parallel to a certain vector, 1 comma negative 2/3 comma 1. It's a line. It runs through the origin. It's a line.